Hi, we are Group 15, and my name is Songhan Wu. Today we will introduce the Kadcyla. Kadcyla is an antibody drug conjugate, but why we need to develop this drug? Because for the traditional method to cure the cancer, like the chemotherapy drug, this drug will not only kill the tumor cell, but also attack the normal cell nearby. So they will result in lots of side reactions. But if we use the antibody drug conjugate, antibody has a high selectivity, so it can exactly attack the tumor cell and results in less side reactions. And here, the figure is the antibody binding with the antigen for our drug. And now I will introduce the structure and the mechanism. The structure can be separated in three parts. The first part is the antibody. Antibody can differentiate the normal cell and the tumor cell because the target antigen is only appears in the breast cancer cells. And the linker is just like a bridge that will connect to the antibody and the payload. Payload is an effective compound which can kill the tumor cell. So here is the mechanism. First, the drug will binding with the antigen, and then it will be eaten into the cell. And in the cell, the lysosome or other protein will cut off the linker and release the payload. So finally, the payload will kill the tumor cell. And based on the structure and the mechanism, we will introduce some problems and a solution to improve this drug.
Hello, I'm Abdul. So let's discuss about the critical issues of the Kadcyla. One is less drug to antibody ratio. Second is free drug availability. And third is it targets only the cells with overexpressed HER2 receptors. So drug to antibody ratio, it tells is one of the critical attribute to consider while designing the dose and therapeutic window. It determines the amount of drug that can be delivered to the target cell, and in turn it determines the efficacy and the safety of the product. In Kadcyla, the antibody has about 88 lysine residues and 4 N-terminus where the linker could bind and the drug could conjugate. So a report on Kadcyla suggested that an average value of DAR is about 3.5. And out of 88 lysine residues, only at least 70 lysine sites were conjugated with the drug. It is reported that they were intercross linking between the lysine, and it only happens if the distance between the two lysine is less than 20 angstrom. So we looked for lysine and the distance between them is less than 20 angstrom. We found out that these are the 5 lysine residues that lie in the close proximity, and the distance between them is less than 20 angstrom. And we mutated one such lysine in such a way that the distance between them is no longer less than 20 angstrom. This way, we are making more lysine available for the drug to conjugate, and we believe this will increase the DAR. So this is the video of the mutated lysine, and you could see here this is the cysteine. Yeah. So the second issue is free drug. The quantity of free drug is an important product quality parameter that is directly related. It is directly related to the product toxicity and patient safety. As we prevented intercross-link, we are providing more lysine for the drug to conjugate, and this way we could reduce the free drug availability that could cause off-target toxicity. And the third is since it is ADC is highly specific and it targets only the cells that overexpresses HER2, we thought we could broaden its horizon by targeting the cancerous cell that do not overexpress the HER2, This could be achieved by making use of the enzymes that are highly active in the tumor microenvironment, like beta glucuronidase. Here it is a matrix metalloproteinase. So we came with an idea like to link a prodrug like DOX to the antibody with mutated cysteine residue, and a peptide linker that could be cleaved by the MMP enzyme that is highly active in the tumor environment. So once the peptide is cleaved by this MMP enzyme, the drug is released and it targets the cancerous cell. So this way, we are proposing three solution to the critical issues of the Catzilla. Thank you. And these are our references.